The crew of Artemis II set a new distance record for humanity from the Earth and returned to the vicinity of the Moon for the first time in more than 50 years. The challenges, danger, and sheer determination to mitigate and overcome these challenges is reminiscent of the heady Apollo days. But firstly, we need to see the immense distances that they will cover. And perhaps to understand the magnitude of the Artemis II mission, we have to look back to its closest historical ancestor, Apollo 8. While both missions represent a first for the respective generations, the technical paths that they take are significantly different due to the hardware and safety protocols of the eras. Let's do an Apollo 8 versus Artemis II comparison. While both missions aim to carry a crew to the vicinity of the Moon, the trajectories and mission objectives reflect different engineering philosophies. So the clearest difference is that Apollo 8 dropped into a low lunar orbit, whereas Artemis II does a free return trajectory only. Now, there is one other Apollo mission that we should mention that has significant similarities to Artemis II. That is Apollo 13, due to the use of a free return trajectory. Apollo 13, however, after a parking orbit or so, launched directly towards the Moon on an initial free return path. To reach its target landing site at Frau Morrow, Apollo 13 performed its MCC, or Mid-Course Correction 1, burn at 30 hours and 40 minutes elapsed time, shifting the spacecraft onto a non-free return trajectory. Then at 55 hours, 54 minutes, and 53 seconds, disaster. An oxygen tank exploded, destroying vital systems and instantly turning the mission into a race for survival. To put the spacecraft back on a free return trajectory, Mission Control couldn't risk using the main service module engine. Instead, they used the lunar module's smaller descent engine as a lifeboat. Even back on a safe trajectory, the crew faced 4 brutal challenges: freezing temperatures, severe water rationing, toxic carbon dioxide buildup, and critically low battery power needed for re-entry. To get them home faster, a crucial PC+2 burn was executed 2 hours after rounding the Moon, shaving nearly 10 hours off the return trip. Fast forward to Artemis II, which used a planned far-side free return trajectory, carrying its crew farther from Earth than any humans in history. 2 historic missions, one where a free return trajectory served as a desperate emergency backup, another where it anchors a new era in lunar exploration. Now, what's the final destination? Well, the final destination is the Lunar South Pole for 3 reasons: water, sunlight, and communication. Water ice is thought to be in permanently shadowed regions, though how much is a little bit of a debate currently. But think about what you can do with water. You need water for everything: for life, for cooling, for rocket fuel. Everything. It really is the game changer. There is, on the ridges, perhaps near the Shackleton crater and other places, near continuous sunlight, and this gives reliable power. It doesn't have the brutal 14-day heat and 14-day night that you'd get closer to the polar regions. Also, on 1 or 2 very high peaks, you have a near direct line of sight for near constant communication. Certainly initially, that would give both high speed and very reliable communication. How does Orion efficiently escape Earth's gravity to reach that free return trajectory? It relies on a classical orbital mechanics hack known as the Oberth Effect, burning at maximum speed for way more energy gain per fuel drop. Let's break it down step by step and see why exactly how NASA uses it for this mission. So simply put, the Oberth Effect is the effect where the greater the velocity of a spacecraft relative to the planet, the greater the increase in kinetic energy, hence total energy, for a given amount of fuel, for a given amount of delta V. Now let's take an elliptical parking orbit. It's stable, and it has two very important points. A point which is furthest away from the Earth, and we call that the apogee, and the closest is the perigee. Now, in this stable orbit, the total kinetic energy and gravitational potential energy are constant. You add them up, and it's constant. Now, gravitational potential energy is based on the distance. The further you are from the center of the planet, the greater your gravitational potential energy. We're going to be a bit simple here. It's a little bit more complex than that. In kinetic energy, the faster that you are moving, the greater your kinetic energy. So at apogee, you're really far away. That means a high gravitational potential energy, hence a low kinetic. When you're at perigee, when you're closest, you have a high kinetic energy but a low gravitational potential energy. So let's see if we can illustrate this. Now, for an impulse burn, and what we mean by an impulse burn is it's the force of the burn is the only significant factor increasing or decreasing the kinetic energy. So for the same amount of fuel, you'll have the same change in momentum, you'll have the same delta V, no matter what your initial velocity is. And that's quite important. Now, let's take a very simple example. We've got something at perigee, which is moving at 20 meters per second. Now, when it moves out to its apogee, it's at 10 meters per second. And we're going to give an impulse burn at both places of 10 meters per second. So, at perigee, it increases from 20 to 30 meters per second, and at apogee, from 10 to 20. And this rocket is very, very small. It's only 2 kilograms, and we'll explain why. Now, the kinetic energy is 1/2 mass times velocity. I've set the mass at 2 because 1/2 times 2 is 1, so therefore it's very easy to calculate the velocity. The kinetic energy is just the velocity squared. Now, let's look at change in kinetic energy. So at perigee, it goes from 20 to 30, so that ends up being 30 squared minus 20 squared, which is 500 joules. Look at apogee. For the same delta V, we end up with only 300 joules. So at perigee, the impulse burn of the same delta V, the same amount of fuel, provides a far greater increase in kinetic energy, hence total energy. And that's the point. And it's that increase in total energy which converts into an increased apogee. The Oberth Effect isn't magic. It's smart physics NASA exploits for Artemis II. With the launch possibly days away, this could be the most efficient escape burn in decades. Have you ever wondered why a spacecraft returning from the moon directly enters the Earth's atmosphere with huge amounts of thermal heating to be taken care of by the heat shield? Why doesn't it enter an Earth orbit, dock with the ISS or other space station, and then the astronauts just return normally? Returning from the moon, the spacecraft needs to slow down by about 3,200 meters per second to enter an Earth orbit which aligns with one of the space stations. This creates a huge fuel penalty. And not just for the stage that needs to slow down. This also creates a fuel penalty for the upper stage that needs to insert lunar insertion to the moon. And it creates another fuel penalty for the huge first stage with boosters that needs to lift the upper stage and the stage which we call the command and service module for the rest of the burns. Artemis I was the first crewed spacecraft to use a skip entry. What is a skip entry, and how does it differ from the lifting and the ballistic entries? Now let's look at the 3 trajectories. Now the ballistic entry has no lift, and it comes relatively straight in. In fact, it still takes over 1,000 kilometers inside the atmosphere. The lifting entry, this is what the Apollo did. It does have an element of lift, but it remains within the upper atmosphere, but it extends both its time and its length of re-entry. Now, the skip entry, such as by the Orion, skips back outside the atmosphere, not by much, there is lift. This greatly extends its distance, and Or extending the time of re-entry, we reduce the peak heating rate and structural stress on both the astronauts and spacecraft.